Welcome to School of Computing. In today's session, we will implement AVL tree using C. In one of our previous sessions, we have discussed in detail about AVL tree and the various operations involved in AVL tree implementation, especially the rotations. So in today's session, we will try to understand the implementation part of AVL tree. So in order to implement AVL tree, we need to create a user defined data type called as node, and the node comprises of four members. One is the data. Data can be of any type. In our example, it is integer. And of course, two pointers, left pointer and right pointer of type the node itself. So struct node star left star right. So left pointer will be pointing to the left child and right pointer will be pointing to the right child. Every child is a node again, and hence the pointer should be of node type. And we know very well AVL tree is a height balanced tree. So in the AVL tree concept, height plays a very important role. Any binary search tree is called as AVL tree only when it is height balanced. And in our previous session of AVL tree, we have discussed what is a balancing factor. Balancing factor is a threshold. Height of any node in the tree, in the binary search tree, must be between -1 and +1. Means the height of any node can be either -1 or 0 or +1. Not more than +1, not less than -1. So when the height is in the range of -1 to +1, then the tree is called as AVL tree. So height at every node we have to check, and that's the reason height is another important variable or member in this structure. So struct node, int data, then left and right pointers followed by height is an integer variable. So we begin with our node definition which we have done. Now let's move on to the main function. So we need to look at our entire implementation, right, as collection of functions. So first I have defined my structure, my node type. Then in the main function, I have created a variable called as root, struct node star root equal to null. You can make this root as a global variable also, nothing wrong in it. I am creating couple of variables called as choice and value. Choice is to run my switch case to take user input and call the appropriate switch case. Value is an integer variable in which I will ask user to enter the data. Now look at the while loop. It seems to be an infinite loop because while 1, when we say while 1, it is an infinite loop. Always the condition is true. So I'm using this infinite loop to create a menu driven program where a menu will be displayed every time with the options insert, display, in order, exit, and then I'm of course asking a user to enter his choice. So in the choice variable we will be collecting the user input and then we invoke the switch case. So since the while loop is an infinite loop, I don't want my program to run into an infinite loop. So every time I'll show a menu to the user, and when user says exit, means when the user opts for exit, that is option number 4, then I will call a built-in exit function in C to come out of my program and terminate the program. If I don't know how to terminate the program, then this while loop becomes an infinite loop. So you should be little careful when you are writing conditions like while of 1. So moving forward, in this switch case, I have case 1 which is for insert operation, where I am asking user to enter some value and I'll collect it in a variable called as value, and then I call the insert function and I am passing two parameters to the insert function. The two parameters to the insert function are root comma value, and insert function returns again a pointer of type node, which is I am collecting it in my root variable. So if you observe carefully, insert function takes the root as input and also returns the root as the return value. The reason why insert function is taking root as input and why again it is returning the root, the reason is, in order to insert a new element in the AVL tree, I need to start from the root. I need to identify where exactly the element will fit. Then what I will do is, if at all there is an imbalance, I may be applying rotation operation to convert that imbalanced tree into a balanced AVL tree, and in that process the root node may get updated, may get modified, and hence after every insert operation, insert function returns you the address of the updated root value. Every time the root node may not be updated, but there is always a chance that the root node may be updated whenever an insertion operation is done, and hence during an insert operation, to begin the insert operation I need the root node, and after insert operation I will convey the latest updated root node. Sometimes it may not be updated, but during an insert operation there is always a possibility that the root node gets updated if at all there are some rotations involved. That's the reason insert function takes the root node as input and also returns the root node or the root value as the return type. Break is a keyword to come out of the switch case so that it should not continue with the second one. Display function, and if I want I can even print the output in an in order sequence. And exit, this is a built-in function in C called as exit of 0, which will terminate the program. This will help me out to come out of that infinite loop. And if the user opts anything apart from 1, 2, 3, 4, then the default case will run and it will print invalid choice. Now the core logic of the program lies in the insert function, and hence we need to observe the insert function carefully. So to begin with, the insert function is taking the root node and the user input, the integer value, as the inputs. So whatever is the current root node, that is copied into node, and the value entered by the user will become the key. Value part is now copied into key. Now if node is equal to null, if node is equal to null, return new node of key. So if you observe carefully, new node is again a function. It's a separate function which is being called when root node, when the node is null. So when the node will be null, when you are calling an insert function and you are passing the root node as input, when it will be null only when the insert operation is being done for the first time. First time when you are inserting a value into your tree, then this if condition will be true. In all other cases, the if condition will fail. So first time, suppose if I am inserting, then the root node will be null and return new node. New node is another function. So if you observe the pattern, insert function was called by main, and insert function is calling new node function, right? So this is an important observation, and one need to understand the context switch. Means from main there is a switch to insert, from insert there is a context switch to new node. So this function call and return values, so you need to observe carefully, you need to observe carefully. So if you observe here, so from main function we have called insert function. So what did we pass from main? We have passed root comma value to the insert function. What insert function has done? So root, first time we are inserting, so root is copied in node variable, value is copied into key, and since node is equal to null, means first time we are doing an insert operation, insert function is calling another function called as new node by passing the key. So please understand the pattern. From main we are calling insert function, from insert function we are going to new node function. Let us observe the code and let us try to digest it. So return new node of key. So I need to go to new node function now. Let me see what is there in the new node function. It's a very small function with 3-4 lines code. Observe. So what new node function is doing, it takes that key and the key gets copied into a variable called as data. Now struct node star node is equal to malloc. You know very well what malloc does. Malloc is a dynamic memory allocation function. It will create a node for you because malloc size of struct node we have written. So we are asking malloc to do memory allocation for how much memory we want, for one node. So what will happen now? Malloc will create a node. So it will look something like this. It will look something like this. So what malloc is doing is it will create a node for me. It creates a node, means somewhere in the main memory, somewhere in the RAM, memory allocation is done. This is a node, sir. This is a node which got created now. So what will be there in the node? There will be a left pointer, one element, right? Data is one element, right pointer is another element, and height is another element or member. So these are the 4 members in the newly created node. Of course, in every node these are the 4 members. Now what will happen? What will happen? Let us assume that this is the node. So in the data column, whatever value you have passed, for example from main you have passed 30, that 30 will be copied into key, and the same 30 is passed to new node, and the new node function copies that 30 into data column or data part of the node. Left and right pointers are initialized with null. Left and right are initialized with null. We are initializing height with 1. Initially we are initializing height with 1. So this is my newly created node in which there are 4 members. Left pointer, right pointer are null. First data item is 30 and height is initialized to 1, and this piece of memory, this entire piece of memory, this is the node, right? So this is the node for which memory allocation is done. So this node will have some address, right? That address, let me call it as 1024. Now coming back to the code, coming back to the code. So if you observe, root hyphen data equal to data, that in this data, this variable which is there in right hand side is the parameter, and node hyphen data means the data member of node, means the one which we have seen in the structure now. So 30 gets copied into the data part, left and right pointers will be initialized with null, height is assigned as 1, and see the last line, this is important, return node. So what is being returned? It returns the address of the node. What is the address of the node? 1024. Now again look at the diagram. So when I say return the node, this address 1024 will be returned. So this entire new node creation was done by which function? New node function has done all these things, right? So new node function returns what? It returns the address of newly created node 1024. To whom it will return the address? New node was called by insert function, so new node returns the address to insert function. So it's a return journey. Main called insert function called new node. So new node has returned this 1024 to insert function. Now what I'll do now, I'll trace my code. Look at the code, return node. This is the last line in new node. So what I will do, when I say return node, I'll go back to the caller. So who called me? Insert function called me. So I'll come to insert function, see this line, return new node of key. So actually what happened, this new node is a function call. You know very well, it's a function call. This new node is a function call, and new node function has returned what? It has returned 1024, this address. So that entire function call is now replaced with the address. Now read this statement, return 1024. To whom I should return this 1024? To the one who called you. Means who called insert function? Main has called insert function. So what is the pattern you need to observe? The point to be noted, point to be observed is, now once insert function received this address 1024, what insert function is doing? It is returning 1024 to main function, because main was calling the insert function. So if I go back to my code, so when I say return new node of key, return 1024, just now we have seen. So insert function is now going back to main with its return address. And look at this line. What is the return type of insert? It is returning you some address of a newly created node, and root is a variable of type struct node pointer, so it can collect. So on the whole, this entire line will look something like this. So 1024 is the address of a node created by new node function, which returned it to insert function. Insert function has again returned it back to main. So root equal to 1024. So before the insert function, root value was null. After the insert function got executed first time, root node is 1024. So please understand the pattern. I hope you are following the way we are tracing the code. So finally what happened? finally what happened? So if you observe, we started our journey from main, right? So when root was null, you know, root was null initially, then main has called insert function by passing root comma value. We assumed root because it is null, so it is null. We assumed value as 30, so insert function was called. And inside insert function, what happened? If node equal to null, we were calling another function called as new node. So what new node function has done? New node function was called by passing 30 as the input. This new node function actually created a node for us, right? So this is left pointer null, right pointer null, height is 1, data is 30. This is the node which was created by new node function, and its address is, let us say, 1024. So what new node has done? New node has returned this 1024 to insert function. Insert function has returned this 1024 to main function. So finally what happened? That return value 1024 was collected by main in the root variable itself. So finally root became 1024. So next time when I call my insert function, and next time this function call, for example, second time I am calling root comma value. Let us say second time I am calling it. So second time, what is root? Already one node is there, and what is the latest value of root? 1024, means root is now pointing to newly created node. Suppose I want to insert 40, means second time when I am calling insert, I am passing the latest root value and I want to insert 40. So accordingly the insert function will decide. Now already one node is there, so if condition will not become true, so it will come to the else part. There we will see how this 40 need to be inserted, where 40 need to be inserted, right? So this is how we trace our code. Yeah. So again I am calling insert with the root comma value. Root is this time 1024. It's not null now. So let me call insert function again. So this time what will be copied into node? 1024. What is key? 40. Now let me trace the insert function. If node is equal to null, is it null? This time it is not null because already there is for one element and the node value is 1024. So it's not null. So this if condition will fail and this new node function will not be called. I'll come to the next step. If key is less than node hyphen data, what is key? Key is 40, we are assuming, right? 40 is less than node hyphen data. What do you mean by node? The current node 1024. What data is there in that node? 30. 40 is less than 30? No. So even this if condition fails, I will come to the else if part. 40 is greater than 30? Yes, condition is true, and this line number 75 will run. So observe this line number 75. 40 is greater than 30. Yes. I am calling insert function, but look at the parameter. I am calling insert function. Node hyphen right is the parameter. What is the current node? 1024. Node hyphen right means current node's right side pointer value. Key is 40. Another important point to be noted is I am inside insert function. I am calling insert function. It's a recursive function call. Function calling itself. I am inside insert function. From insert function I am calling insert function again. Now what do you mean by node hyphen right? Node hyphen right means presently node is, what is our present node? What is our present node? Our present node is this one. This is our present node. Now this is left and this is right. So what is node hyphen right? It is null. So I am calling insert function again from within the insert function. So what are the values I am passing? Node hyphen right. What is there in node hyphen right? It is null, comma, key. What is key? Key is 40, right? So null, comma, 40. So we are calling insert function again. Interestingly, we are calling this insert function from insert function only. So our first insert function was insert of 1024 comma 40. In this insert function, since 40 was greater than 30, this insert function led to creation or call of another insert function, insert of null comma 40. Why it is null? Because 1024 is my first node, its left and right pointers are null, and this is node hyphen right, so this is null. So what will happen now? Again insert function code will run. This time again first if condition will become true again, node equal to null. So what will happen when I say node equal to null? Then new node function will be called. Whenever a new node function will be called, what new node function will do? We know that very well. What new node function will do? We know that very well. What this new node function will do is it will create a node and it will put null in the left pointer, null in the right pointer, height is 1. This key 40 is copied here. This is newly created node, and you know in the new node the last step is return the node, right? Return its address. For example, if this newly created node's address is 2048, let us say. So new node function, so this insert as called new node. This new node function created this node, and this new node function is returning now. What it returns? It returns the address of newly created node 2048 to the insert function, which called new node. But this insert function was called by another insert function. So what will happen? This address will be now propagated and returned back to the previous insert function. So where it will, now let me show you where it will go. So what will happen? This insert function led to creation of another function call, which is node hyphen right means null comma 40. So another time insert function will run, and this if condition becomes true, new node function got executed, and this new node function created another node, and whose address we are assuming to be 2048. So it will look like this. So node hyphen right equal to 2048. What do you mean by this? What do you mean by this? The meaning of this one is we already had a node, right? We already had a node whose address was 1024. Null was the left pointer, 30 was the data, right pointer was also null, height was 1. Now if you observe the code, it was written like this, right? Node hyphen right is equal to insert of node hyphen right comma key. So this entire line insert function created a new node whose address is 2048, which is now copied into node hyphen write of previous insert. So which node this node hyphen write refers to? Our first node 1024. Its write value, which was null, is now substituted by 2048. So what will come in this null value? In place of null value, 2048 will come. What do you mean by that? Meaning of this one is 30 is my first node and its right pointer is pointing to 40. So it is something like this. So it is 30, and what is the right pointer of 30 pointing to 40? So this is what the insert function has done now. Right? So I hope you are able to trace the code properly. Now suppose if I am trying to insert anything less than 30, then what will happen? This if condition will become true and node hyphen left will come into picture, so that the newly created node will be pointed by the left pointer, so that it creates proper BST, binary search tree. Values less than 30 will come on left side, value greater than 30 will go to right side. Now till now we have seen how this insert function's logic is running, but we did not observe the another part of insert function, only inserting whether on the left side or right side, that portion we have seen. But another important point in AVL tree is we need to calculate height at every time, and if the height of the tree is not balanced at any node, then we have to do rotations. So how we are calculating the height? Every time when a new node gets created, we initialize height variable with 1, but we need to calculate height at every node. Further, what we are doing is, look at this one, in the insert function itself, node hyphen height is equal to 1 plus 1 plus max of height of node hyphen left comma height of node hyphen right. So what is the role of this max function, and why we are saying 1 plus? These are the two important things. Let me explain it so that it will be clear for you. For example, I have a tree something like this. 40 has 2 children, 50, and this is 35, and this is 60, let us say, and this is 15. Now suppose I need to check whether this is a height balanced tree or not. I need to calculate height at every node, and you know very well how to calculate height. Height at a given node is calculated as height of left subtree minus height of right subtree. Now height at leaf nodes will be 0 because there is no left and right subtrees, right? So height at 3 leaf nodes we have, it is 0. Now let us find height at 50. At this node, what is the height? Left subtree minus right. Left side I don't have anything, so it will be 0 minus right side I have 1 edge. So 0 minus 1 is the height. Similarly, at this particular node 40, what is the height? Left minus right. Left side I have 1 edge minus right side I have 2 edges. It is minus 1. So if you observe, height at 15, 35, 60 is 0. Height at 40 and 50 is minus 1 and minus 1. Let me calculate height at 30, the root node. Left minus right. Left side I have only 1 edge, so it is 1 minus. Now here right side, please observe how many leaf nodes we have. Do we have a single leaf node? If we have a single leaf node, there is no confusion. You just count the number of edges from that node to the leaf node. So in left side I have only one leaf node and the number of edges are 1. So height of left subtree is 1 minus. In the right side I have two leaf nodes 35 and 60. Now I need to see from 30 to 35 how many edges I need to visit. So from 30 to 35 the number of edges are 2, and from 30 to 60 the number of edges are 3. So whenever you are calculating the height, you have to take max of, so you have to take max of 2 comma 3. So that is the purpose of that max function, max of 2 comma 3. So max of 2 comma 3 is, maximum value is 3. So it will become 1 minus 3. Answer is minus 2. Height at root node 30 is minus 2, and of course it is imbalanced. Then we need to apply rotations. So in AVL tree, we just need not insert nodes on the left and right side. Every time we also need to check the height. We also need to calculate height. Whenever a new node gets inserted, height of the tree will change, height of the node will change. So that's the reason you need to calculate height, and you also need to check whether it is balanced or not. So we have two functions in our program. One is height function to calculate the height, and another important function called as get balance. It will check the balancing factor on every node. So this get balance function will tell me whether there is an imbalance or not, and wherever there is an imbalance, immediately we will do rotations. You know very well how to perform rotations. Now in the previous instruction, you have seen the instruction was like this: 1 plus then max of height of left subtree, max of height of, what did we write, max of, yeah, 1 second, max of height of node hyphen left comma height of node hyphen right. So why are we doing this 1 plus, why this 1 is being added? That is another important point to be noted. So why are we adding 1? So please observe here, what is the height of the overall tree? For example, what is the height? Now when we look at the tree, we look at the tree as levels, right? So how many levels we have? This is, you know, this is one level, this is another level, level 2, this is level 3. So when you look at the tree level wise, right, you got 3 levels. Number of levels are 3, but the height of the tree, overall tree I am saying, but height of the overall tree is 4, right? So whenever a new node is being inserted, or when a new node gets created, or when a new child gets created, to be more specific, when a new child gets created, it increases the level. And if you look at the levels, if number of levels are 3, height of the overall tree will be 3 plus 1, 4, right? So that 1 plus in our instruction plays a very important role in finding the height of the tree as well as height at every node. So moving forward, so this is an important instruction where we look at the height and then we call the balance function. Get balance is a function. So what this get balance function will do? Get balance function returns a number which is collected in balance variable, right? Now let us go to get balance function and we will come back to our insert function. Look at this get balance function. If n is equal to null, this will be true only when the tree is empty, right? Otherwise, return height of n hyphen left minus n hyphen right. So it is very simple statement. Get balance function will return height of left minus height of right subtree. That is how we calculate balance factor at every node, right? Height of a node is height of left subtree minus height of right subtree. So height function is also there, because if you observe in get balance, I am calling height function. So height is a function applied on node hyphen left, node hyphen right. So height function, we will just go through height function also. So what is this height function? If it is tree is empty, it returns 0. Otherwise, it returns n hyphen height. If you remember in the beginning, we were inserting 1, or we were initializing 1 in our height variable within the node. Now whenever we call this height function, it returns n hyphen height. Now why this is important means this is called recursively. This is an important point. Don't think that height is 1, so always it returns 1. It's a recursive call. So what will happen is, if you have a root node followed by a left node, another left node, every child returns this value, and this is getting accumulated, or the cumulative summation is done to find the height. So don't think that it is simply returning the height. It simply returns the height, but it is being accumulated because of the recursive nature of this height function. So this is how the height and get balance function plays an important role inside the insert function. Now look at this one. So get balance returns me what? It returns me a number, and if that balance is greater than 1 and key is less than node hyphen left hyphen data, we need right rotation. So friends, please observe this. This is a condition where LL rotation problem occurs. So you know very well, four types of rotations are possible. So in order to identify what type of problem has occurred, or what type of problem created an imbalance, then accordingly we do a rotation. So if it is LL rotation problem, then I'll do a right rotation. If it is RR, I'll do a left rotation. If it is LR problem, you know very well it comes under double rotation. I'll be doing a left rotation followed by right rotation. Left rotation should be done on the successor, you know very well. So node hyphen left followed by right rotation on the node itself, the imbalanced node. Similarly, RL problem, right? Again it comes under double rotation. Do a right rotation on the successor, node hyphen right, and left rotation on the node itself. So four conditions represents four different types of rotations. Let us check at least one function so that you understand these rotations. And for both left and right rotations, we have the function. So let me take one example of RR problem. Okay. So let us take this RR problem example. For example, 30 is one node. Imagine first time I have inserted 30, then I have inserted 40. So is there any problem when there are only two nodes? There should not be any problem, because height at leaf node is 0 and height here is minus 1. Left minus right. Left side of 30 we don't have anything. So 0 minus 1, it is minus 1. Now please observe here 30, 40. When I am inserting another right child 50. Let us check what is the height at 50. Leaf node, it is 0. left child minus right child, height at 40, left minus right, left side I have nothing, so it is 0 minus 1, minus 1 is the height, and here it is left minus right, 0 minus 2 edges on the right side, it is minus 2. So when I added 50, it created an imbalance. So this is a case where we have an imbalance, and the imbalance was created because of 50. So what type of problem it is? How to identify the problem? First you have to see from the root node which side the problem has occurred, left side or right side. Problem has occurred on the right side, so R. First alphabet we will be written like this. Okay, problem occurred on the right side. Problem occurred because of whom? Problem occurred because of a newly created child. Who is that newly created child? 50. Is it a left child or right child? 50 is a right child. So write another R. And hence it's a RR rotation problem. RR rotation problem. So what we will do in a RR rotation problem? We do a left shift. So when I do a left shift, what will happen? 40 will become root, 30 will become left child, 50 will become right child. So let us check whether the same thing is being implemented by this. So when I say left rotation, I am calling left rotation function. I will be calling a left rotation function. So let us check, let us trace our code. Okay, so did you notice balance is less than minus 1? We got imbalance, no, minus 2 we got. So when we will get a negative imbalance, especially we get negative imbalance during RR problems only, right? RR as well as RL. You get a positive imbalance in LL problem and LR problem. So here balance is less than minus 1. Yes, I got minus 2. And key is greater than node hyphen right hyphen data. What do you mean by this? What do you mean by this? This is the node, right? This is the node. And what is 40? It is node hyphen right. And this is the key which I am trying to insert. So key was greater than node hyphen right hyphen data. Node hyphen right means the right side node of 30. Node is 30. Node hyphen right means 40. So right node hyphen right hyphen data means 40. 50 is something which I am trying to insert, which is key. So key is greater than node hyphen right hyphen data. Yes, key is greater than that. So what need to be done? Imbalance is there and it's a RR problem, so I should do a left rotation on node. Node means what? 30. So let us go to left rotate function. Right, so this is left rotate function. X, what is this X? The node, nothing but 30 in our example is passed. Now struct node star Y is equal to hex hyphen right. What is there? What is X? X is representing 30. 30 is hyphen right is 40. 40 is now stored in Y. Y hyphen left. 40, do 40 have any left child? No. So it is null. So T2 is getting null. Now please observe here, Y hyphen left, X is copied into Y hyphen left. What is Y? What is Y? Y is 40 now because X hyphen right. So please observe here, X is nothing but 30. 30 is hyphen right means 40, which is stored in Y. Now 40's left is getting X, means what do you mean by that? 30 is becoming left child of 40, which is nothing but left rotation, and X hyphen right is equal to T2. What is T2? T2 is null. X hyphen right, 30 is right. Do I need to have a right child for 30? No, so it will be null. 40 became 30 became left child of 40, and 40's right child will remain, 50 will remain as 40's right child. So these two lines, line number 48 and 51, was actually doing that left rotation for me. So this is simple left rotation function. Now you may also observe there are two important lines, 54 and 55. What we are doing, since with the tree got modified, since the structure of tree got modified because of the above code, there may be change in the heights. That's the reason we are calculating heights again, because whenever we do a rotation we need to calculate the height to check whether it further creates any imbalance or not. If the imbalance is resolved, then it is an AVL tree. So this is left rotation. Similarly, the right rotation will be done in the other direction. So I hope you got a fair understanding of the entire code, and for display purpose what we have done is we called the display function in which we are using a function called as print given level root comma I comma space. So what we are doing in print given level function, it is very simple. You just go through the code, probably you can understand, but still I'll be explaining it. Suppose if the input series is like this: 30, 40, 50, then 25. So what will happen? 30 gets inserted, then 40, no problem till 40, but the moment I insert 50 it creates imbalance, you know very well, and left rotation need to be done. So it becomes 40, 30, 50. Then we try to insert 25. So 25, where it gets inserted here. Let us calculate heights to check whether it creates imbalance or not. Height at leaf node is 0, so 0 here. Height at 30, left minus right, left side I have 1 edge, right side I don't have anything, 1 minus 0 it is 1, and height at 40 is 2 minus 1, because 2 edges on left side, 1 on right side, 2 minus 1 it is 1. So when I insert these values, it is 40, the final tree will be like this: 40 will be the root node, 30, then 25, and on the right side I'll have 50. This is a balanced AVL tree, height balanced AVL tree. Now what we have done in our display function is, in order to create this kind of output, what we have done is, for example, this is our output screen. What we have done is, we have created a variable called as space, and what we have done is, we know very well that in any tree, in the root node we will have only one element, and we want that root node to be in the center of the screen. So we gave 8 spaces to print our root node, means 40, let us say. Then what we have done is, if this 40 got printed after 8 spaces, if 40 got printed after 8 spaces, the left child of 40 and the right child should be, it should give me a look and feel as if it is a tree. So left side what we have done is, we have done -4. So 8 minus 4 is 4. After 4 spaces we have printed the left child, and right child, means left child is -4, right child will be printed with +4 spaces. So 8 minus 4 means somewhere here 30 gets printed. 8 plus 4 means after 12 spaces 50 gets printed. So this 40 got printed at 8th pixel or the 8th position. After 4 spaces 30 got printed in the next line. After 12 spaces 50 got printed, and I continue this logic down the line also. So if 30 has any more children, where they will be printed, 30 is printed after 4 spaces, right? So 30's left child will be printed again half of it. So 30 got printed after 4 spaces, 30's children will be printed minus 2, means half of it, and 30's right child will be plus 2 spaces, so that it will create me this kind of look and feel. So 25 gets printed here. Of course there is no right child, so I don't need a right child here. So just to organize my output like this, we created a small logic for spaces. We are organizing our nodes based on spaces. So the root element will be printed after skipping 8 spaces. Its left child will be printed after skipping 4 spaces. Right child will be printed after skipping 12 spaces. And in second level, the children of 30 left will be printed with minus 2, means after 2 spaces. If at all there exists a right child, should be printed plus 2 spaces, means if 30 is at after 4 spaces, means right child will come at 4 plus 2 after 6 spaces. Just to organize this output, that print given level function was used. So if you just go through it, probably you can easily digest it. So let me quickly show you the print. This is the print given level function. So if root equal to null, for I equal to 0, I less than space printf, I am printing 8 spaces, right? So you may ask me, where did you calculate the value of space? See here, space is equal to 1. This is a shift left operation. H minus I plus 1. H represents height of the tree. Height of the tree. Height of the tree in our previous example was height of the it was 3, right? So 3. 3 minus I is 1 initially. 1 plus 1 it is minus 1 plus 1 it is negotiated, becomes 0. H is 3. So this 1 will be shifted left 3 times. So 1, if I shift left 1, it will become 2. Then if I shift left it again, 2 will become 4. Then third time 4 will become 8. So 1 into 2, it is like multiplication by 2. Left shift is same as multiplying by 2. So 1 is multiplied by 2, it becomes 2. If I do it again, it will become 4. If I do it third time, it will become 8. So space variable gets calculated based on this logic, and when the loop runs next time, I value will become 2. 2 minus 2 plus 1, so it will be minus 1. So 3 minus 1, it will become 2, means in the next level this number of spaces will become 4, and in the next level it will become 2. Like that, the space control is managed with the help of this for loop. And in print given level function, right, we are simply printing the root hyphen data, and of course the balancing factor also. So let me just run this program. So gcc avl demo.c, and my output got collected in avl output. So let me execute the output file avl output. So insert, let me insert 30, Then again I am calling insert function, I will insert 40. Then again I will call insert function, I will insert 50. Then again I will call insert function, I will insert 25. Then I will call my display function. So 40, 30, 25, 50. 40 is the root node, left child is 30, right is 50. Same example which we have discussed. So I am just trying to give you a feel as if it looks like a tree with the help of this space control. Along with the data, we are also printing the height at that node just to confirm that our AVL tree logic is working fine, and we are also printing, means whatever tree I have printed is a perfect AVL tree, so we are printing height also, so you need not cross check by again calculating the height. So this is what is the output of the program. So let me terminate it, exit. So you have seen exit option to terminate the program, otherwise it was running continuously asking me for entering the choice, so it will continue like that. So I hope you got a fair understanding of the program. So to summarize, in this session we have applied structures and linked list for implementing AVL tree, and we have also examined how AVL tree serves as self and height balancing tree with the help of rotations. So I hope you can also implement AVL tree program by using C programming language, especially using structures, self-referential structures and linked list. And we also know the applications of AVL tree. So binary search tree has certain limitations. So to summarize, BST had a problem. What was the problem? When the BSTs are skewed either left or right side, their performance gets degraded. Performance is close to linear search, so which is very very poor. So in order to address that problem, we need height balanced trees, and AVL trees are height balanced trees, and with the help of rotations we can ensure the height is balanced in AVL tree, and hence AVL trees are very very good for such applications. And I hope this discussion and examination tracing of the code had made it more clear for you, and you can also implement AVL tree on your own. Thank you.